Hello everyone and welcome to the sixth video that will be part of the series about the Go programming language. And today, as promised in the last video, we will look at a little bit more into floats and also in general about numeric types in Go. Because yes, we look at integers and we briefly mentioned the floats, but in Go it turns out that there are many other numeric types that can come quite in handy in some situations where, for example, you want to occupy less space in memory. So if you want to make a memory efficient program, then you might not want to use int every time. So we will start this video as promised with an introduction to floats. So what are floats actually? So floats in general stands for floating point numbers. And what floating point number actually means, so in this video we want to go like super in depth, super low level into how floats are stored in memory, but we will just give a little bit of important notions about floats, and also we will explain on a high level how floats are stored. So a float again stands for floating point number, and this basically means that the point, the point that basically separates the decimal part with the integer part of a number that is not an integer is stored. So it is not fixed, but it's rather floating. So the use of floating point arithmetic was chosen because of many advantages that it has over fixed point arithmetic. However, one of the disadvantages that floating point arithmetic has over fixed point arithmetic is that floating point arithmetic is considerably less accurate. So this is why often when you will work with floats, and for example you make comparisons between floats or you will sum them, you will notice weird behaviors, and that is completely fine. That is basically inside the we could say a nature of the floating point arithmetic. And so if you maybe had to write, I don't know, a computer algebra system or something like that, and you wanted to have a more precise way to add, for example, non-integer values, then you could probably, if you wanted to, implement your own fixed point arithmetic system. But that will be pretty time consuming also because you will want to optimize it. And as an alternative, you could just use a third-party library. So with this said, we just introduced a little bit what floating point number means. And let's see now how floating point numbers are stored in memory. So we're going to go over just regular floats, because there are floats that are stored in 32 bits, and in Golang these are called float 32, and we introduced it also in the previous videos. But there's also floats that are stored in 64 bits, and these are called float 64. So if you come from C, but again, if you don't know C, don't worry about it, then you would probably recognize these are floats and doubles. But again, don't worry about it if you're not familiar with C. So with this said, let's now see how floats are stored in memory. So now imagine you have a decimal number, such as, for example, 2.5. Okay, then 2.5 in decimal notation that has an integer part that is 2 and a decimal part that is 0.5. So how the computer stores this in memory is in the following. It converts this into binary in the following way. So decimal part just gets converted into binary in the regular way. So it is equal to 1, 0 in binary. And why? Because, well, 1, 0 is just 1 times 2 to the 1, which is 2, plus 0 times 2 to the 0. And this is, as in total, is just equal to 2 in decimal. So it converts 2 into binary, 1, 0. Well then, for the exponent, the process is a little bit different. You basically multiply the exponent by 2 until you get 1. In this case, you immediately get 1, and so this is just 1. And the number 2.5 translated into binary is just 0.1. Another example could be, for example, 7.25. So again, 7.25, 7 in binary is just 2 plus 4 plus 1. So it's basically 1, 1, 1. But 25, so 0.25, what you do is you multiply by 2 once, so 0.25 times 2, you get 0.5. So you take 0. Then you multiply 0.5 by 2, you get 1, and you take 1, and then you finish. And so the end result is 111.01. And so this is the conversion, some examples of conversion from decimal notation to binary. So now we know how we can convert decimal numbers from base 10 to base 2. But now how does the computer store these decimal numbers actually? Because, well, this process of conversion from base 10 to base 2 is quite important in the process of the storing of floats into memory. And we will see now how this actually comes into play. So suppose again we have a number such as 7.25. So already said that this number gets stored as 111 upon 0.01. Yes, it should be 111.01. And now, how does the computer actually store this number? So the computer stores this number by separating it into two parts. And these parts are called the significant part and the exponent. Also, the significant part is also known as the mantissa portion. So just as a notice, you will want to know that sometimes, because sometimes it's called mantissa portion. And it allocates a certain number of bits for the exponent and for the mantissa portion, because you know that computers basically store stuff in memory using bits, which is binary, just means binary digits, which is a 0 or a 1. So they store it in base 2 basically. And now, but we do not know yet what these words mean basically, because we say, okay, significant part, exponent, but what even is that? So the definition of significant part and exponent will become clear once we know in which form the computer transforms this basically this decimal number in binary. In particular, it will transform our converted number, which is 111.01, into the following form. So it will basically be 1 point some digits here times 2 to some number. Now, the digits after the 1, so that we denoted with these minus signs, is the mantissa, is the significant part of the number. Whereas the natural number n, to which we raise 2, is the exponent. And this is basically how a computer saves into memory a bit. So it basically just saves these parts after the 1, and then it saves the exponent to which you raise 2 and multiply the number. In this case, our 7.25 would just be 1.1101 times 2 to the second power. Why? Well, because by multiplying 1.1101 by 2, so 1.1101 by 2 yields 1.101, and then multiplying it by 2 again yields 111.01, which is our original number. And so this is how the computer stores it into memory. And we also talked about that the computer can allocate either 32 bits or 64 bits, also depending on the architecture of the computer, for this floating point number. And for the float 32, it will allocate 32 bits. And these 32 bits will be basically segmented in the following way. We'll have 8 bits allocated for the exponent, and we will have 32 bits allocated for the significant part. And then actually you will say, well, what about the last bit? We now have 31 bits, allocated. What about the last one? Well, 1 bit will be allocated for the, basically the flag for the sign. Because of course you need to specify if the number that we saved is a positive or a negative number. A flag for the sign is also present for integer values stored in memory. For example, if you store a integer inside of memory, so a value int, where you don't have to worry about all this mantissa and exponent part, you just have an integer, so something like that. Well, the way in which you store it is you say, okay, if it's a positive, I'm gonna set the 1 bit to denote the sign. So if it's positive, it's gonna be 0. If it's negative, it's gonna be 1. And then the remaining, for example, if we're storing a number in 64 bits, the remaining 63 bits will be devoted to the actual number, to the storing of the actual number. So the maximum number that we can store in 64 bits for a signed integer will be 2 to the 63 minus 1. Whereas the maximum number that we can store in 32 bits for a signed integer will be 2 to the 31 minus 1. Now suppose that we only care about the actual value, so the absolute value of a number, and not about the sign. Then we will free basically 1 bit for its storage in memory. And so the range of numbers that we would be able to represent would be from 0 to 2 to the 64 minus 1. And so this is for what are known as unsigned integers stored in 64 bits. And we will see at signed and unsigned integers in this video, because we will cover numeric types. So this is basically roughly how floats work. And for 64 bits, so for float 64, you will have again 1 bit stored for the sign flag, then 11 bits for the exponent, and then 52 bits for the significand. So this is on a very high level, meaning that we do not like dive super deep into it, how the computer stores floats into memory. And if something is not super clear about it, you can just comment in the comments and I will give some clarifications about it. But even if maybe something's really, you really struggle to understand something about this part, don't worry, because you will not need it in your daily programming life, of course, especially at the beginning. But it's good that maybe you just have an idea of how floats work. Maybe just to not, we could say, become discouraged if you ever encounter errors working with them, because you will of course have a lot of errors when you will work with floats and also doubles. So now that we have covered floats, we're ready to see how to declare them in and initialize them in Golang. So the first way in which you could declare a float variable would be to just say var, then its name, which is an identifier, and we also covered the rules for how to give names to variables in the last video. So it can be like AB1, and then we decide its type. So we have seen that there are two types of floats that we can store basically in Golang. That is float 32 and float 64. So float 32 is a 32-bit floating point number. And for example, let's store inside it the number pi, so 3 to a precision of 2 decimal places. So let us try to use the printf function and print out its type and its value. Yeah, and let's insert IB1 and then AB1. So let's see. As you can see, we got float 32 and then 3.14. So what if we now set it equal to float 64? Oops, okay. Then we get that it is of type float 64. Now, we've covered in the last video, in the previous videos, the concept of type inferring. So we have seen that if we not specifically specify a type for a variable, but we assign it at declaration, then the compiler can deduce on its own the type of the variable. Let's see what happens if we basically declare and initialize a variable AB1 and set it equal to 3 for example, another, we will say decimal number such as 2.75. Let's see what type will it give. So if we run it, then we get float 64. And this is because actually the default type that Golang will give to a variable by type inferring, in the case of floats, but we will see that this actually applies also to integers. So the amounts of bits that we'll allocate depends also on your computer architecture. So if you have a 64-bit computer, then the default type by type inferring that it will give to a variable of decimal type will be float 64. But if you have a 32-bit computer, then that will be a float 32 variable. You can try on your own and see what kind of computer you're working on at the moment. So with this said, we now know how to declare variables of floating point numbers, so floating point number type. But now let's see other types of integer variables, because so far we've only seen variables of the type int. But there's actually many integer types, and let's see all of them now. So the first type that we'll see is int8, and this type represents an 8-bit signed integer. What this means is that the computer for this data type stores 8 bits in memory, allocating 1 bit for sign and 7 bits for the actual number. So the maximum value that this type can assume in absolute value will be equal to 2 to the 7 minus 1. Why? Because, well, with 7 bits we can represent a number of maximum 2 to the 7 minus 1 if you're a little bit comfortable with binary arithmetic. And if you do a calculation in decimal, this would be the 27. However, we can also drop the 1 bit that we allocated for sign, because with this type here, we can also represent negative numbers, meaning that with int8 type, we can also represent, for example, a number such as minus 97 or minus 9. But what if we want to drop the sign, so we only care, for example, about positive numbers, and then we can declare a uint8, which means an unsigned 8-bit integer. And this, the range here is augmented. In particular, it goes from 0 to 2 to the 8 minus 1, meaning that the maximum value that we can represent is 255, and the minimum value that you can represent is 0. well, then there are also other sizes for integers. For example, there's a int 16, and this is, you can guess it, it's basically a 16-bit signed integer. And there's also, for example, a uint 16, and this is just a 16-bit unsigned integer. And now again, if you know binary arithmetic, it would not be too hard to understand that the maximum number that you can represent with a uint 16 would be 2 to the 16 minus 1. But you can also only represent positive numbers. Whereas with int 16, you can represent also negative numbers, but the maximum number that you can represent is 2 to the 15 minus 1, of course, in this case, in absolute value. Then there's also the int 32 type, which is a 32-bit signed integer. And again, here the maximum value in absolute value is equal to 2 to the 31 minus 1. And then there's also its unsigned counterpart, which is uint 32, which is again a 32-bit unsigned integer. And the maximum value that you can represent with it is 2 to the 32 minus 1, but it's only positive values. And then lastly, we have int 64 and uint 64. And here the range of values with uint 64 is basically 0, 2 to the 64 minus 1. Whereas with int 64, the range of values is minus 2 to the 63 minus 1 up to 2 to the 63 minus 1. And so these are all the main integer types. So then you might say, well, but where does int fit in here? Well, int just depends on your computer architecture. It might be int 32 or int 64, depending on the size of your registers. The registers is just a type of memory inside your CPU, but that is very fast to access. And so this determines your architecture, whether it's 64 bits or 32 bits. Then there's also another type that is uint, which just like int defaults to uint 32 or uint 64, depending on your computer architecture. Then there's also another important names for these variables, and that is that might come in handy specifically maybe if you come from Java. And the first one is byte, and byte is basically equal to uint 8, whereas the keyword rune is exactly equal to int 32. So if you declare a variable with the keyword byte, or basically it's the same as declaring it with the keyword uint 8. So with this said, we have now seen at many types of integer types. And now that we know how to declare integer variables, let's see how to combine them via operators, arithmetic operators. And there are 5 main ones. The first one is addition, and we use the symbol plus for it. Then there's subtraction, and we use the symbol minus. Then there's multiplication, and we use the symbol star. Then there's division, and we use the slash symbol. And then there's remainder, or also reduction to congruous modulo n, and we use the percentage sign. So let's see how we can use these types. So for example, let's declare an int 16 variable. So var a int 16, and let's set it equal to 400. Then let's declare another variable b, again of int 16 type, equal to 561. So now let's let's print out with println their difference. And let's see what happens. So, and we get minus 161, which is precisely the difference. And you can see that you can do the same pretty easily with the plus instead of the minus. And by running, you get their sum pretty trivially. But let's now see what happens if one of the numbers is of a different type. So for example, let's declare one with int 32, and the other let's keep it in 64 and 16. Let's see what happens. And as you can see, we get an error because we are summing numbers with different type. Now let's try and also see multiplication. So let's now convert both of them to int 32. Let's set this equal to, for example, 3, and then let's print out their product. And as you can see, this yields their product. And lastly, let's also see add division. But for division, I'm going to show you something. Look at this. We get an integer. And what does that mean? Because if you try to divide, for example, 400 by 3, then you get that this is not actually 133, but it's 133 point something. And well, then what is happening? And here, this is actually If you come from C, you're already familiar with this concept. If not, then I'll explain it briefly. But here, the division operator in Golang does not represent actual division, but it represents integer division. That means that it returns the quotient between two integers. If you know the log division algorithm, also known as the Euclidean algorithm, when you divide two integers, you basically, so for example, an integer b by an integer a, then you basically find integers values q and r such that you can write b as a times q plus r. Basically, by performing integer division, that is b divided by a, you're returning the value q. And basically, the value q that we got is precisely the quotient between the integer division between b and a. Because if you have b, between a and b. If you have a, for example, 400, you can precisely write 400 as 3 times 133, which you can verify is 399, and then you add 1. So 1 is the remainder. And to get the remainder, we use the operator percentage that we defined above. So if we, in fact, print out a percentage b, now let's see what we get. Oh yeah, sorry, I forgot to comment those lines out. I don't know why, but okay. So with this set, okay, and as you can see, we get 133 and 1, as expected. So with this set, we have seen the most important arithmetic operations for integers. But what about floats? So with floats, you can add numbers in exactly the same way, as well as subtract them and multiply them. So if we, for example, declare a variable pi of type float64 equal to 3.14, and then another variable, for example, a, again float64 type equals to -5, then if we print out with print ln pi times a, we exactly get their product. But as you can see, and as I also said before, you might see these kind of anomalies. You could see these weird 0, 0, 0, zeros and then a 1. That's because, again, that's a problem with the floating point number representation in memory in your computer. That's precisely because this 14 here cannot be, when we basically multiply by 2, if you remember that algorithm procedure that we did, cannot be basically reduced to 1 at a certain point by multiplying iteratively by 2. If you, in fact, for example, if you place 25 instead of 14, let's see what happens. We get -16.25, because this number can actually be represented with a finite number of bits inside memory. That the same cannot be said for 14. And this is why 14 gave that weird number and whatever. So, and then between floats, there's actually also division. And division yields the result that you want to see. In fact, this gives -0.65. And so, with this said, I think we have said enough about arithmetic operations and integer types as well as floating point number. And for this reason, I will conclude this video here.